Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about resonance. This is the season finale of What's the Big Idea, and it's appropriate that we're going to end up on what is literally a very exciting topic. For in resonance, the idea is that you have a variety of physical systems in the world. They could be a girl on a swing, or a boy with a wine glass, or a bridge in Tacoma Narrows, Washington, or an MRI, magnetic resonance imaging machine, somewhere in a hospital. And in all those cases, there are systems that have a natural frequency of vibration. And when you excite systems at their natural frequency, you can build up big amplitudes of oscillation, often to spectacular effect. So let's dig in. So to begin to understand what's going on with the phenomenon of resonance, it's useful to first start talking about a situation that we'll refer to as damped harmonic motion. And a damped harmonic motion is just a little bit of added twist to simple harmonic motion, in that now, instead of just having a mass on a spring, you also have some friction in the system, some so-called damping. So in this idealization of a system that would execute damped harmonic motion, we have a mass on a spring that's rigidly supported at one end. So if you pull the mass down and let it go, the mass will oscillate up and down. But the other end of the mass is attached has a little plunger here, and there's some sort of thick liquid perhaps. And so as the mass oscillates up and down, there's a significant frictional force. So the amplitude of oscillation dies off. There's damping, and that just means that the mechanical energy that was initially in the system dissipates due to the damping force that is being applied. And the situation will vary depending on how big the damping force is. So there's some parameter B, which sort of governs the strength of the frictional force in the system. And the bigger B is, the more quickly the oscillations will die off. So we imagine that you start off, you displace the mass in amount x sub m, and you let it go, and the oscillations start off with amplitude x sub m, but then gradually the amplitude dies off. So these dotted lines here sort of show the decay of the amplitude of oscillation under damped harmonic motion. And it's important to note here that the system has what I would call a natural frequency of oscillation. That is, the frequency of these oscillations, which is basically determined, as you know, by the value of the spring constant and the value of the mass. So you take the square root of k over m, and that gives you the angular frequency, the natural angular frequency of oscillation. And then the next thing you want to imagine is that you, instead of having a rigid support here, imagine that you can, hold on to this with your hand and wiggle the support up and down at some frequency, which we'll call the driving frequency. And what you find if you do this is, so omega d is the driving frequency, the frequency or the angular frequency at which you're wiggling your finger up and down. And what you'll find is that the system falls into a oscillation at the driving frequency, but the amplitude of the oscillation depends on the relative value of the driving frequency compared to the natural frequency of the system. So this graph shows us if omega is the natural frequency, the frequency that you get when you have just damped harmonic motion, and you adjust the driving frequency, so you adjust the frequency at which you're wiggling your finger. When you get close to a situation where the driving frequency matches the natural frequency of the system, you can build up very big amplitudes of oscillation. And particularly if you're in a situation where there's not much damping, because if there's not much damping, whatever energy you put into the system tends to stay there for a long time. So that enables you to build up a large amplitude of oscillation over very many cycles. And if all this seems esoteric to you, let me point out that it actually is a situation which everybody, just about everybody, has experienced in their lives, particularly starting as children. So think about what happens on a swing. You pump your legs, and if you pump your legs at the right frequency, you build up a big amplitude of oscillation. And if you think about it, what's really happening is you're pumping your legs at the same frequency as the natural frequency of the system. So if you stop pumping, you sort of swing back and forth at a certain frequency, and the way you get up to a big amplitude of oscillation is to kick your feet at just the right frequency. If you look at a very young child on a swing, they don't quite get this, and they will furiously pump their legs back and forth and wonder why they're not getting anywhere. And that's because they're not pumping at a frequency close to the natural frequency of the system. So, a famous example of this, which people often point to, is the Tacoma Narrows Bridge collapse. This was a situation, this was in the 1940s in Tacoma, Washington, where there was a bridge that didn't have much damping in it, and there was a wind that would happen to be able to excite the bridge at its natural frequency, and it built up these enormous amplitudes of vibration just because the frequency of the driving force was very close to the natural frequency of the system, and we end up with these spectacular images. Famous images of the collapse of the Tacoma Narrows Bridge. And here's another sort of part of the story. There was a physics professor who was actually trying to study this from the University of Washington, and he narrowly escaped um, his demise because his car, he abandoned his car on the bridge, and shortly thereafter there was a total collapse of the bridge. It's amazing. This is solid steel that is vibrating to these enormous amplitudes, so it's really quite remarkable phenomena. And let's wait just a minute, and we'll see the actual total collapse of the bridge coming up. There we go. Here comes total collapse. There it goes. Bye-bye Tacoma Narrows Bridge. So they learned some important engineering lessons, that it was important to put damping into the system if you don't want it to behave like that. Closer to home, there's a demonstration that we do in a lab that we do when we're in person, in which we can break a wine glass with a sound. So the idea, you take an ordinary wine goblet, and I'll say in a moment how we choose the wine goblet. But we set it up. This is behind this piece of wood here is a fairly ordinary loudspeaker. And we have a system in which we can generate a sine wave of a certain frequency that we amplify with a pretty impressive audio amplifier to drive the speaker. And it's pretty loud when we do this. We actually have a piece of plexiglass. This is in a box, and we keep it in a piece of we put a piece of plexiglass in front, both to protect ourselves when the wine goblet breaks, but also to keep the sound down a little bit so we don't annoy our neighbors. And then what we do is to find out what the right frequency is, we have a little microphone here, and we measure the frequency of, we ping the goblet, and we measure the frequency of the sound, and we get an idea of what the right frequency to set the sine wave generator is. And then what we do is we actually turn on the sound generator, and we position the microphone right next to the glass. And when we get close to the resonant frequency, the glass starts shaking, and we can actually see on an oscilloscope a change in the amplitude of the vibration, because now we're picking up not only the sound coming from the loudspeaker, but the vibrating glass. Once it starts to vibrate, it's making its own sound, and we can detect that, so we can see very accurately when we're getting close to the right frequency. And it turns out that to do this, you really need to get the frequency very precisely set. So that's one thing. And then you got to pick the right kind of wine goblet. Okay, so this is how we look for unsuspecting victims to break. You give it a ping, and that's the tone that you're looking to run the frequency, the speaker at. And what I'm listening for when I pick a good wine glass is one where the ringing lasts a long time. That means energy that you put into the system stays there for a long time, and that's what you need to build up a big amplitude of vibration in order to get the glass to shatter. And those of you who are musically inclined will recognize the pitch of a typical wine glass. It's well above sort of concert A, where you would tune your musical instruments. Concert A is at 440 hertz. The goblets that we use tend to have frequencies of about 800 hertz. And so when you do get the glass shaking, it's shaking very fast, 800 times a second. You're not going to see that with your eye. But another thing we do to make the demonstration much more interesting to watch is we illuminate the goblet with light from a strobe light. So the light is flashing on and off at a frequency that very closely, it's not exactly at the resonant frequency, but it's pretty close. And the effect of the strobe light, when you illuminate periodic motion with a strobe light where the frequency of the strobe is close to the frequency of the motion, the effect is to sort of slow down the apparent frequency of the motion. So the video that I'm going to show you, it's going to look like it's in slow motion. It's actually filmed in real time, but because we're illuminating the light with a strobe, illuminating the glass with a strobe light, it appears that everything is in slow motion. So you really get to see how much the glass can bend before it breaks. It's really quite impressive. So I'll play the video for you now. The sound is a little bit annoying. I'm going to leave it on just so that you get a sense of how loud the sound has to be in order to get a wine goblet to break. Whoops. Let's start at the beginning. There we go. Pretty cool. That video, by the way, was recorded, I think it was the very first time I taught Physics 107, circa 1988, many years ago. And it was really quite exciting when that wine goblet broke. Now, we had all this fancy equipment to break a wine glass, and we had to get the frequency exactly right. But I can't resist showing you this YouTube viral clip, 21 million views, of a boy breaking a wine glass with his voice. So let's watch. Whoops. Okay, let's start at the beginning because you really have to see the whole thing.
My name's Chase, and I live in California, and I'm going to try to break this wine glass by only my voice.
So the straw is there, so he's trying to sense when the glass is actually starting to vibrate. The straw starts moving if he hits the right frequency.
Did you video it? Yeah.
Pretty amazing, pretty cool. Okay, so let's finish up with an example of resonance that's recent and also close to home. This picture here shows Wellesley College sophomores Jiatong Yang and Cora Barrett working in the laser lab where I do my research. We are working on a project in quantum physics to study a particular defect in the structure of diamond. This is called a nitrogen vacancy center. So this is the size of just a couple of atoms, an imperfection in a diamond crystal. And it turns out that we can do magnetic resonance experiments on just one atom-sized defect using this home-built apparatus. This is a type of microscope that we've built, and we can conduct what is called an optically detected magnetic resonance experiment. So the results, this is just recorded just in the last week by Cora and Jiatong. They are adjusting the driving frequency of a microwave source. So the frequency that this system resonates at is in the gigahertz range, and just in the vicinity of about 2.87 gigahertz. This system will respond to a driving frequency, and it turns out we're monitoring the intensity of some visible light that is sensitive to changes in this in the state of the center. And when we excite it at the driving frequency, we get a change in the intensity of the light. And not only that, but Cora and Jattung have a little magnet here, and as they move the magnet closer to the system, the dips here get farther away, so the system is sensitive to external magnetic fields. So anyway, this is an example of how the phenomenon of resonance actually is very useful for studying physical systems in the world. And that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.